Hello everyone. In this class, we'll look into the topic on simultaneous material and energy balance under steady state condition. This is for a steady state condition operations. Let us take an example of a process where a reaction is not there, but we have to consider material balance and energy balance simultaneously. As an example, we'll consider drying operation, which is quite commonly used in downstream operations in biotechnology. So here you have material balance as well as energy balance coming into picture. Let us look into the concepts in detail. Let's go ahead. Now here we are with the simultaneous material and energy balance concepts. Now understand one concept that normally when we do the material balance for learning purpose, we learn it separately. Energy balance, we learn them separately. But in reality, what happens is this material and energy balance are dependent on each other. So in a realistic situation, you cannot keep them separate. You need to work out with the material balance, you need to work out with the energy balance. Some of the aspect or unknown terms under energy balances, you can solve it using the values obtained from the material balance. So because of that, you cannot have them as a separate concept, you need to learn them as combined concept. So here is one approach where we are taking an example for a simplest reason that it is quite commonly used in biotechnological processes, that a drying operation. A drying or dehydration, by definition, we are just removing the water by evaporating it, by removal of water, that water from a solid surface or even a liquid surface, normally a food, which is a quite common product, with the purpose of obtaining a solid product sufficiently low in moisture or water content. So the content of water in that food or the substance what we are drying is called as a moisture content, right? We call it as water content or moisture content. So you have the slab or the material over here. You need to remove the moisture out of it. Initially it is at a high moisture content. At the end you want to have a low moisture content in that particular material. For that, what you do, you are supplying a hot air, a hot stream of air. Okay, the hot stream of air, it has got its own moisture content. Air is also having moisture content, means the air can carry moisture within it. Moisture means water vapor. Okay, so the water vapor is a part of the air that can flow over the solid surface because of the difference in moisture content. Means moisture content in the solids is higher than the air. So what will happen, the moisture content will transfer from the solids to the air, and that's how the moisture content in the solids will decrease. So over the time, what will happen, the air which is moving will take away the moisture along with it. In other words, the moisture content of air increases from inlet to outlet, whereas the solids, the moisture content will decrease from inlet to outlet. That's what is our requirement. So there are two components coming in, air and the solids, food otherwise, right? One which has to be dried, the two of components come in and two of them go out. One is in the gaseous phase, one is in the solid or liquid phase. Air does not get into the solids or solids does not get into the airs. Another way of drying is you are just drying using the normal heating process. You can heat that entirely as it is and the vapors are removed from that particular uh, the solids. Let's look into some definitions, some terminologies not commonly we use in drying before we get into the further concepts. One is humidity. The humidity is moisture content of air. We generally call it as absolute humidity. In other words, as humidity, it is the mass ratio of water vapor to dry air. When I say dry air, when I say normally air, air contains the dry air plus moisture in it or water vapor in it. You imagine something like a sodium chloride solution. Sodium chloride is a solid. Sodium chloride is dissolved in water. So you have water as solvent, sodium chloride as a solute that is dissolved. We call it as a solution of sodium chloride, right? Now equivalently, very similar to that, air is a solvent for a moisture. Moisture is a solute dissolved, or in fact it's not dissolved, it is associated here. So it is associated with the dry air. So the dry air plus moisture gives you the wet air, right? Now for the simplicity or for the calculation purpose, we use something called as dry basis. That means we consider for all the purpose dry air only. So along with the dry air, how much moisture is there? On the basis of dry air, all calculations we perform. So here onwards, you come across a word called as dry air. Dry air means it's a reference value that you are taking. It is associated with the moisture. Don't undergo the misleading concept that when I say dry air, air is always dry. No, air will contain the moisture, but that moisture is explicitly mentioned. Okay, so actual air comes in, has got dry air as well as moisture. Along with that, it comes as one unit. For analysis purpose, we are keeping them as separate as dry air and moisture, right? So the unit of this absolute humidity is kg water vapor per kg dry air. So here is the definition: mass of moisture per mass of dry air. If at all we require it to be in a unit of moles, molar ratio, so it is the moles per moles dry air, we can write it. But if normally we define it in the mass quantity, so you can multiply with the molecular weight of water and molecular weight of air, right? Moles into molecular weight gives you mass. Why I have written this 18 and 29 as a molecular weight, so this is equivalent, right? Now moles per mole, that is molar fraction, or the mole fraction is equal to volume fraction. Volume fraction, that is equal to pressure fraction. That's what we have seen for the ideal gases. Now here the air can be assumed equivalent to an ideal gas, and it is present at a total pressure of P. Each molecule, that is either it is moisture or dry air, it is present at its own partial pressure. You know the Dalton's law, the individual partial pressures, when you add it, it will be equal to that total pressure. So the pressure exerted by the water is Pw, pressure exerted by the air is P air, and they are called as partial pressures. When you add them together, it will be the total pressure in which air is present. Usually we take 1 atmospheric pressure air. So P normal equal to 1 atmosphere, 101,325 Pascal. Now instead of writing molar ratio, I can also write in the form of partial pressure ratio. This is the partial pressure of moisture. P minus Pw is the partial pressure of air. Instead of writing it as partial pressure of air, we write total minus the partial pressure of moisture, because P is equal to Pw plus P air. Using this concept, we have written it. This is highly useful because we can solve some problems based on this equation. Let's go ahead with the another definition called as saturation and relative humidity. As the name says, it's a humidity similar to absolute humidity, but it's relative. There is something called a saturation concept coming into picture. In terms of salt, you know the concept of something called a saturation. We came across this in crystallization concept, right? So the solubility we have come into picture here. So what you had there, the salt, it can dissolve up to a particular concentration in the solvent at a given temperature. At that given temperature, if you add anything extra, it will not dissolve. The extra amount what you are trying to dissolve will come out as a crystal. That's what is the concept in crystallization we learned about saturation. Exactly similar, you can apply the concept here. You have the dry air, it will at a given temperature, you can have some amount of moisture in that, right? But it can have moisture up to a certain limit, that's saturation. More than that moisture, if it is trying to take it, it will condense because phase change will occur, right? So here it will be moisture will turn into liquid, vapor to liquid formation. That is nothing but condensation. So the moisture capacity of air is the saturation capacity, maximum up to which it can hold, right? So that is called as saturation condition. We also call it as that particular temperature at which happen is called as dew point. We will come across that later. So the moisture and I mean maximum moisture you can accommodate in a dry air is saturation condition or saturated moisture. Now in reality, at a given temperature, the air will have some moisture, but its capacity is a different one. Its capacity is higher, a higher value. The ratio between the pressure, the humidity and its saturation value, the ratio between the two in a percentage scale, write it as percent relative humidity, right? So relative humidity means it's a fractional value, percent relative humidity means uh, it's on a percentage scale. It's something like, if I have to equate it to the class marks, a student has a capacity to score 100 marks. That's maximum. More than that, we don't allocate, right? So maximum mark allocated to a student is 100. Now, in that exam, he can score anything from 0 to 100. That's his actual mark. Possibly he scored 80 marks, right? That is 80%. So it depends on his maximum limit. And this particular maximum value, it will change in this case. For the case of humidity, air humidity case, the maximum value changes with respect to temperature. As you change the temperature, maximum condition also changes. Similarly, in our examination system, for semester exam you have one maximum mark, for internal exams you have another maximum mark, for in the case of another task or any other assignments and activities, you have a different maximum marks. But any case, when you convert your actual marks with respect to the maximum mark and convert it in a percentage scale, all of them will be on a percentage scale, right? That is relative its maximum marks. That's in the examination system. Now in the case of air, here you, at a given temperature, you have the maximum limit, that is a saturation limit. With respect to saturation limit, absolute present humidity, how much it is, you will verify it, and that's the percent relative humidity. Right? Now you can convert that to the ratio between the partial pressures. So partial pressure of water vapor, that's the moisture, divided by partial pressure of the saturated vapor. Now the saturated vapor water vapor pressure is always called as vapor pressure of the liquid. Okay, so the partial pressure of the saturated liquid. Under saturated condition, the partial pressure is always given a term, it's a standard term called as vapor pressure. In simple word, vapor pressure is the partial pressure of a vapor which is under a saturated condition. Under saturated condition, right? So saturated condition is the keyword here for relative humidity. Then we come across something called as dBT and WBT. In simple, I'll simplify the concept here. So the dBT is nothing but the thermometer that you keep and check the temperature is called as dry bulb temperature. That means it measures the exact temperature as it is without any modification. Whereas WBT, wet bulb temperature, means the thermometer what you have a bulb to it, right? At the bottom a mercury bulb is present. That mercury bulb, let me say I am covering it with the cotton, and so I mean, when I cover it with the cotton, I'm ensuring that the surrounding air is also able to come in contact with the bulb, and I'm making it moist. The cotton, I'm making it moist. What will happen now? There is a transaction between the moving air and that moisture for the transfer of moisture, right? The moisture content in the cotton, moisture content in the air surrounding will make a transaction. That means moisture will move across. After some time, what will happen? The moisture content in the air, moisture content in the cotton, both become equivalent, almost equal. At this point, the temperature in the thermometer, it decreases. It won't go up, it decreases. And that temperature at which you have the moisture content is called moisture content which is saturated with the air, it is called as WBT. In other words, it's a saturation point. It's a saturation point. That particular temperature we refer it as WBT. So when we do the analysis of moisture content in the air, we don't calculate them individually. We have graphical solutions, graphical methods. Graphs are available where dBT and WBT are in connection with each other, and we can experimentally find out dBT and WBT. Based on these two values, we can calculate the properties of air, different properties of air. We can calculate using something called as psychrometric chart or humidity chart. That we will see it in the next video. So one more term comes into picture now, is called as dew point. Dew point is one property of the moist air. This is the temperature at which a saturated vapor converts or changes its phase from the vapor to liquid form, right? So we get in the morning, early morning, dew or mist we see, right? So that's the dew point condition. The temperature is low, such a way that the vapor in the air gets converted to a liquid phase. Yeah, that's it for this class. In the next class, we'll see some numericals on this concept. Thank you.